Let's talk about complex numbers. Consider the quadratic equation x squared plus 1 equals 0. Notice that this is a sum of squares, not a difference of squares. Therefore, we're not able to factor it. So we're sort of forced to go ahead and subtract 1 from both sides. If we do that, we get x squared equals negative 1. And then at that time, we need to square root both sides. And notice we have a negative number under the square root. Well, this has been defined as I is equal to the square root of negative 1. So memorize the fact that I is equal to the square root of negative 1. Note that squaring both sides yields I squared equals negative 1. So we squared both sides. We will get I squared equals negative 1. Therefore, memorize that as well. Memorize these two things, these two formulas or equations. I is equal to square root of negative 1 and I squared is equal to negative 1. Real numbers and imaginary numbers are subsets of the set of complex numbers. So if you look at this egg right here, representing complex numbers. Let's just imagine that's like the universe. If you had to compare it to something, that's like the universe. And we were on Earth over here on the real number system. And now we are exploring another planet. Let's call it Mars. We are exploring the planet of Mars now, seeing what its environment is like, seeing what the different rules are on this planet. So let's first discuss pattern recognition. If I is equal to I, or I to the first power is equal to I squared is equal to negative 1, then what is I cubed? Well, you can break down I cubed as I squared times I, for example. So I cubed must equal I squared, we know, is negative 1 times I. So we know that this is the same thing as negative I. I cubed is the same thing as negative I. What about I to the fourth? Well, you can break that down as well. You can say I squared times I squared. It doesn't matter how you break it down as long as those numbers add up, all right, to the 4. So we know that I squared is negative 1 times another negative 1. So that is a positive 1. So I to the fourth must equal 1. What about I to the fifth? Maybe you want to break it down as I to the fourth times I. Then, well, we just found out that I to the fourth was 1 times I. So I to the fifth must equal I. And you can attempt other ways to break up I to the fifth. It could have been I squared times I cubed, for example, or I squared times I squared times I. All right, so I to the sixth is what would we like to do? I to the fourth times I squared. I to the fourth we know is 1, and I squared we know is negative 1. So I to the sixth must be equal to negative 1. Now what's going to happen is that this is going to repeat itself every fourth cycle. So for example, we started with I negative 1. So I negative 1, negative I 1. Then it started back over. I negative 1. Guess what I to the seventh is going to be? It's going to be negative I. Guess what I to the eighth is going to be? It's going to be 1. So it's repeating itself every fourth one. You see that? It's repeating itself. So it's cyclical. This is cyclical behavior in the imaginary number system. All right, so we have this definition of a complex number. It is a combination of a real number and imaginary number, a plus bi. Notice the real part is first and the imaginary part is second. The imaginary part is attached to the I. That's how you know that it is the imaginary part. So we have examples of complex numbers here. 1 plus I, 39 plus 3I, 0.8 minus 2.2i, negative 2 plus pi I, square root of 2 plus I over 2. So for this one, which is probably the more tricky one, if I ask you what is the real part, the real part here is the square root of 2, right? That is the real part. But if I ask you what is b, the b is not I, it is what's attached to the I. And hopefully you see that that is I over 2, which is same thing as 1/2 times I. So the b would be 1/2 in this case. If we go on here, here are some other examples. 3 plus 2i, the real part is 3, the imaginary part is 2. And for 5, there is no I at all. So the real part is 5, but the imaginary part is 0. And for this complex number, negative 6i, there's no real part. So the real part is 0, considered to be 0, and the imaginary part is negative 6. Now when we add and subtract and multiply complex numbers, it behaves in the way that we added and subtracted and multiplied in the real number system. So for example, 6 minus 4i plus 1 plus 3i, we are treated like we're looking for like terms. So for example, 6 and 1 we can add together, and negative 4i and 3i we can add together. So 6 plus 1 is 7, and negative 4i plus 3i is negative I. So notice I wrote it in the standard way you write it as a plus bi. I wrote the real part first. Now with subtraction, you have to be very careful. Always rewrite it out because you need to distribute the negative through the second part of the expression, right? So you have negative 5 plus 4i now. So now we have 3 minus 5 is negative 2, and negative 2i plus 4i is positive 2i. So again here, don't forget with subtraction, write it all out. Distribute negative 1 through the 6 plus 13i, giving us negative 6 minus 13i. Therefore, 3 minus 6 is negative 3, and 2i minus 13i is negative 11i. Now let's get to multiplying. We know that this is multiplication because there's no sign in between these parentheses. So we are multiplying. We're going to pretty much multiply this like we multiplied two binomials in the real number system, foiling it. All right, so 6 times 2 is 12. 6 times negative 3i is negative 18i. And then we're going to come down here, enter negative 2i times 2, negative 4i, and negative 2i times negative 3i is positive 6i squared. Let me emphasize that because my students usually miss that part. It's I times I, which is I squared, just like x times another x is x squared. Don't miss that. That would be an issue if you forget that. All right, so we have 12, and then we have this negative 18i minus 4i, negative 22i. And now we know a little something about I squared. We know that it is equivalent to negative 1. So we have to replace the I squared with the more simplified answer, which is negative 1. So we are not done. We have 12 minus 22i minus 6. Therefore, we can put that 12 and minus 6 together, which is 6 minus 22i. So our final answer is 6 minus 22i. Now, let's go to E. 3 plus 2i and 3 minus 2i. Notice it's really the same thing except the signs in the middle. These are called complex conjugates. So something special is going to happen when you multiply complex conjugates together, meaning that sign in the middle is different, but everything else is the same. So let's look at it. 3 times 3 is 9. 3 times negative 2i is negative 6i. 2i times 3 is a positive 6i. And 2i times negative 2i is what? So say it before I say it. What is 2i times negative 2i? Hopefully you said negative 4i squared. Again, let me emphasize that squared. Students mess up on that, so don't mess it. Don't mess up on that part right there. That will be the issue if you get it wrong. So now notice that our middles cancel. We have 9 minus 4 times negative 1. We are replacing that I squared with negative 1. That's 9 plus 4, which equals 13. So what was so special? Well, we started with i's, right? We started with i's, but we didn't end with an I. Our answer will not contain an I if we are multiplying complex conjugates together.